in this video we are going to talk about numerical methods to solve ordinary differential equation. Okay, that is chapter 8 from the book. All right, so why do we need the numerical methods to solve differential equation? Is because, as I mentioned in the class, that we cannot solve each and every type of differential equation, right? Only few differential equation can be solved and then can be found the exact solution. But there are many differential equations that cannot be solved. So suppose you want to model certain physical phenomenon, you develop a differential equation, but if you cannot solve that differential equation, then the model does not work, right? I mean, you cannot find out the solution, you cannot find out the result of that differential equation, then there is no point of creating a model. Okay, so can we solve a differential equation other than the method that we learned? Can we get the exact solution of all the differential equation? The answer is no, right? But can we approximate the solution of a differential equation? The answer is yes. Okay, so many differential equations cannot be solved to find out the exact solution, but we can solve to find out the approximate solution, meaning that we can approximate the solution of a differential equation. Okay, so let us consider a differential equation. This is the first order differential equation, dy over dt equals to function of t and y. So on the right side there can be any value of t and y. That can be t y or y square t, any kind of thing on the right hand side, and the initial condition is y at t0 is y0. Suppose this is given. Okay, suppose you don't know how to find the exact solution, you don't know how to solve this equation by the methods that we learned so far. So how do I approximate the solution of this? Okay, that's the thing that we want to talk here. So to find out the solution of to approximate the solution of this differential equation, there are many methods. Okay, so the simplest method is called Euler's method. This is very basic method to approximate the solution of a differential equation. So this method basically uses the tangent line approximation or the linear approximation to find out to approximate the real solution of a differential equation. Okay, suppose this is the differential equation. On the right hand side there is f function of t and y, so we don't know what that function there can be anything, any combination of t and y, right? And y at t0 equals to y0. So suppose y equals to phi t is the solution of this equation, and we don't know how to find out that solution, but suppose that is the solution. Okay, now what we do to find out to approximate the solution of this differential equation is we start with the initial condition. So what is the initial condition here? Initial condition is at t0 the value is y0, right? At t0 the value is y0. So what we do is we try to draw the tangent line at t0 y0, right? Because one of the point is t0 y0, right? t0 y0 is one of the point on the solution. You see that? Because the solution will be y equals to phi t, right? So how does that look like? We don't know that yet. Suppose that is the we suppose that the solution look like that. Okay, so I want to approximate this solution using the Euler's method. So what we do first is we try to draw the tangent line at this point t0 y0. So how does the tangent line look like? That's what the tangent line look like, right? So what is the equation of the tangent line? So the equation of tangent line at t0 y0, that is at the given point, right? At that point is, what is the equation of tangent line? Y minus y0 equals to, the slope is f at t0 y0, right? Because that is the slope is the derivative, right? So that is the slope f, but this is at t0 y0, so you write f at t0 y0 and then you do t minus t0. You see that? This is the equation of this tangent line. Okay, this is the equation of this tangent line. So we use the given point to find out that tangent line, and we use this tangent line to approximate the height of the solution at t1. We'll do that later first. But first, write down this in the simple form. So you write y equals to, you can write y0 plus function at t0, y0, and then times t minus t0. You see that? So this is the equation of the tangent line, this tangent line, okay, at the given point. You see that? Now our goal is to find out, to approximate the solution y equals to phi t. So how do we do that? This is the first point of the solution. We will find out another solution, another point on the solution. We'll find out another point. So we continue that way, okay? So how do I find out, how do I approximate the height of the solution or the y value of the solution at t1? So at t1, let us suppose that the height of the function is y1, okay? So what we do is we find out that point is t1, y1, right? So what do I do that? Is you just replace t by at t equals to t1, let y is y1. So that's what we are assuming there, okay? That point is t1 comma y1. So how do I approximate that value, y1 value? Is I use that tangent line to approximate the height of the solution. We don't know, to approximate the height of this solution, that solution, and we don't know what is the equation of this solution. What we do is we will approximate at each point of t1, t2, t3, t4. We will find out the y value, or we will approximate the height of the solution using the tangent line, okay? So if you plug in that point here, you'll get y1 equals to y0 plus f of t0, y0, and then times t1 minus t0. So we are replacing t by t1 and y by y1. You see that? Okay, similarly, what we do next is we want to approximate the height at t2, right? So to approximate the height at t2, we don't use the same tangent line. We will first find the tangent line right here at this point, okay? So how do this is the approximation of the tangent line, okay? Because your curve will look like this. You see that? Your approximated curve will look like this. Like that, okay? So basically what we do is we do exactly the same thing, exactly the same steps. Now what we do is we will try to approximate the tangent line at the point t1, y1. We find out the tangent line at the point t1, y1, okay? So what we do is at t1, y1, so equation of that tangent line will be, equation of tangent line is y minus y1 equals to function at t1, y1, because we are trying to find out at t1, y1, right? And then t minus t1. You see that? If you simplify as we did for the t0, y0, you will get y equals to y1 plus f of t1 comma y1, and then t minus t1. Now to approximate the height at t2, we use that red tangent, right? We will to approximate the height of the function, height of the solution at t2, we will use the tangent at t1, okay? That is basically, you see there will be the error, like some error there. That's the error. But the error will be minimum if your T1, T2, T3 are very, very small, right? These partitions or these width are very, very small. In that case, the error will be very, very small, okay? So at t equals to t2, let y value is become y2, okay? So what do you get then? So if you plug in that, you will get y2 equals to y1 plus f at t1 comma y1, right? And then t2 minus t1. You see that? Look at this pattern. You see, if there is y1, all of them are zeros except that t1, right? If there is y2, all of them are y1, one before, and then that is t2, okay? So if you have to approximate for y3 the same way, how the y3 look like? It will be y2 plus f t2 y2, and then it will be t3 minus t2. It will look like that. You see that? All of these subscript are the same except that t. Okay, that is whatever there is. If there is y2, there will be t2. If there is y3, there will be t3. So if you continue this process, so what do you get? I want to generalize this. If I write yn plus 1, okay, how does that look like? It will look like yn plus f at tn comma yn. You see that? And then tn plus 1 minus tn. This is called the Euler's formula. Okay, this is called Euler's formula. This is called the Euler's formula. Okay, now if you assume that this length between t0 and t1, t1 and t2, t2 and t3, t3 and t4, they are all equal. If you assume this length equal, then that length will be, this will be h, 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 h. Let us suppose that the difference or the length of each of the sub interval is h. Then how does that look like? This will look like h, right? This will look like h. All these will look like h, and then that will also look like h, right? So how does the final version of the formula look like? The final version look like this: y of n plus 1 equals to yn plus, this will be h, right? So h times f of tn yn. So this is also the Euler's formula. This is the simplified version where we call the step size, okay, that h is the step size. If you take the step size equal in all of those subinterval, okay, then this is the Euler's formula. Okay, if you continue that way, it will look like at this point, right, and then the line will look like that, and then you approximate the height by that, and another will be like that, and another will be like that, and so on. You see that the approximation of the real solution or the true solution approximation will be almost the same as the true solution, but it is not the same. But when can you make very, very close is if h is very, very, very small, then that approximated curve will get very, very close to the true solution. Okay, so we'll do some example, but this, don't forget this is the Euler's formula, and this formula we call explicit formula. Why it is explicit? Because on the right hand side, see, on the left hand side there is yn plus 1. Okay, on the right hand side, all of them are different from yn plus 1. So the right hand side does not depend on yn plus 1, right? So the right hand side has different than yn plus 1. So this is called explicit. Explicit means yn plus 1 is written in the in terms of yn and tn's here, right? So this is called the explicit formula, Euler's formula. Okay, so our idea next will be, if there is a differential equation given, what we will do is the first thing, given thing will be t0 and y0, right? And then we'll find out t1 and y1. So how do I find out t1? So t1 will be approximated by this. Okay, look at this one. What is t1? T1 can be written as t0 plus h. You see that? What is t2? T2 is t1 plus h, or you can say that t0 plus 2h. You see that? h plus h. So it is t0 plus 2h. What is tn? Is t0 plus nh, right? Because if you continue that, you will get t3 equals to t0 plus 3h, t4 equals t0 plus 4h, and then tn is t0 plus nh, right? What is tn plus 1? It is similar, right? t0 plus n plus 1 times h, right? Whatever you want. So you can basically find out the t0, t1, t2, t3 values, okay? So the h will be given to you, or you assume h there, okay? The step size, h you will assume. But what we do next is, by using that this tn formula, or tn plus 1 formula, and then that yn plus 1 formula, what you will do is you will find out t0, y0 will be the given one, right? And use this formula to find out t1 will be approximated by that, or t1 will be given by this t0 plus h, right? And to find out y1, you will have to plug in n equals to 0. That will give you y1 equals to y0 plus h times f of t0, y0. So f will be given to you as well. And then you find out t1, y1. and then also find out t2, y2, and then continue that way. So after you find out all these points, you plot these points like that, and then plot those. Just join that. That will be the approximation of the solution of the given differential equation. Let us see this example. Use Euler's method to approximate the solution of dy over dt equals to y with the initial condition y0 equals to 1 by taking the step size h equals to 0.5. This is given. Okay. Also plot the true and approximated solution. So what do you think? What is the true solution of this? I mean, most of the time you don't know the true solution, okay? But in this problem, this is easy question, so you can actually find the true solutions, right? How do I find out the true solution? So solution is to find out the true solution. What you do is you do dy 1 over y dy equals to dt, right? So now integrate natural log of y equals to t plus c, right? So what is y? Y is e to the t plus c. So let's do c1 so that you can write e to the t times e to the c1, right? So it is c e to the t. Now if you use the initial condition y0 equals to 1, what do you get? You will get here 1 equals to c times e to the 0. So c is basically 1, right? So what is the final true solution? Y of t equals to e to the t. This is the exact solution. Okay. Now we will need this to plot, to answer this plot. Okay. Now we want to approximate the solution by using the Euler's method. So to use the Euler's method, let's list what is given. What is f of t y? It is just y, right? Because dy over dt equals to f of t y. So this is y. What is t0? t0 y0 is given by 0 1, right? Because see, y at t0 is y sub 0, so that is 0 and 1. So also what is given is h is given as 0.5. So what is the Euler's formula? yn plus 1 equals to yn plus h times f of t0 y0, right? So if you do that, what do you get? Yn plus h. Let's write down h is, we know the value of h, but yn values will change, right? So h is just 0.5, right? What is f of t0 y? Sorry, this is t and y. Okay, so this is the Euler's formula, right? Y sub n plus 1 equals to y sub n plus h times f of t and yn. So what is the value of f? F is basically, f is given as y, right? So you can write 0.5 times yn. So this is yn plus 1 equals to yn plus 0.5 yn. So we will use this final form. Remember that how do I find out the tn? Okay, so we wrote that tn equals to t0 plus n times h, right? So, and also let me write down that yn plus 1 there. So what is n? What is h in our case? So here tn equals to t0 is 0 plus n times h is 0.5, right? You see that? So basically tn has formula n times 0.5. Okay, and also let me write down that yn plus 1 formula here. Yn plus 1 equals to yn plus 0.5 times yn. So we will use these two formula to find out the points, and then we'll write that in the table. Okay, let us create a table for that. So table with 3 columns. Okay, so this is n. I will write down tn here. This will be yn, like that. Okay, now, so first of all, what I want to do is take n equals to 0. When n is 0, you will have t0, right? What is the value of t0? T0 we got, t0 is 0, and when n is 0, it will be y0, right? So y0 is 1. This is what we got. So what is the point? That point is basically 0 1. That is the first point in the solution. Okay, that is the first point in the approximation of the solution actually. Okay, now let us take n equals to 1. When n is 1, you will get t1, right? How do I find out t1? Look at here. T1 will be 1 times 0.5. That will be 0.5. So what will be y1? So we want to find out y1. To find out y1, you will have to take n equals to 0 here. You see that? When you take n equals to 0, then you will get y1 equals to y0 plus 0.5 times y0. Okay? So it will be y1 equals to y0 plus 0.5 times y0. So what is y0? Is 1 plus 0.5 times 1. That will be 1.5, right? So that will be, so y0 is 1, y1 equals to 1.5. So the point is 0.5, 1.5. This is what you get. Similarly, when you take n equals to 2, you will get t2. T2 will be n equals to 2, right? So T2 will be 2 times 0.5. That will be 1. You see that? And then Y2. How do I find out Y2? You will have to take n equals to 1 to find out Y2, right? Y2 will be, Y2 is basically Y1 plus 0.5 times Y1. You see that? Because to find out Y2, you'll have to pick n equals to 1. So y1 plus 0.5 times y1. So what is y1? Y1 we've got 1.5 plus 0.5 times 1.5. Okay, so 1.5 plus, what is 1.5 times 0.5? I think it is 0.75. 0.75. What value did you get then? 1.5 plus 0.75 will be 2.25. You see that? Similarly, take 3 for n. So you'll get T3 equals to 1.5 here because 3 times 0.5, right? And then Y3 will be how much? Y3 is Y2 plus 0.5 times Y2, right? That will be 2.25 plus 0.5 times 2.25, right? Now multiply those two. So you will get 2.5 plus 0.5 times 2.25. So 2.25 times 2.25 plus 0.5 times 2.25. If I do that, I get 3.375. So that will give me 3.375. Let us plug in those points. That point is T2, Y2 is 1, 2.25. That is 3.375, right? So it will be 1.5, 3.375. And you continue that, okay? You continue that way. So what the question also asks to find here is, you want to plot both the real solution, the true solution, and the approximated solution in the same graph. Okay, let us graph the true solution and the approximated solution together. Okay, so how do I do that? Is what I want to do here is draw the t-axis and the y-axis. Okay, so this is the t-axis, this is the y-axis. So t0 equals to, let us first plot the y equals to e to the t. So y equals to e to the, so this is, let's say this is 1, okay. Let's do, this is 0.5, this is 1, this is 1.5, this is 2, and then so on, right? So when you plot the y equals to e to the t, when t is 0, it is 1. This is one of the point, right? You see that? This is 1 point. And when t equals to 0.5, then e to the 0.5 is how much? E to the 0.5 is 1.64. Let me put 2, 3, 4. So 1.64, maybe somewhere here, right? And then next is when t equals to 1, e is 2.72, right? You will be 2.72 somewhere here. When t is 1, it will be y1 equals to e to the 1. So that is e is 2.72. And next is when e is 1 point, when t is 1.5, then that is 4.48. At 1.5 it is 4.48. Somewhere here, and so on. Let me join that. So this is y equals to e to the t, right? This is the true solution. Now I want to plot the approximation. So how do I do the approximation there? So what are the values? At 0 it is 1. This point is the same. At 0.5 it is 1.5. At 0.5 it is 1.5. Slightly bigger, smaller than that, right? At 1 it is 2.25. At 1 it is 2.25. Slightly smaller than that. At 1.5 it is 3.375. At 1.5 it is 3.375. Somewhere here. You see that? This is the approximation of the solution. Okay. You see that? Your approximated solution is very, very close to the real solution. It is not like really close, but how can I make it better is, if instead of taking the h equals to 0.5, if you take h equals to 0.1, or you say h equals to 0.01, it will be very much close. Okay, so it does not matter what function is given on the right hand side. It may be very complicated, hard to integrate or hard to solve, or any easy function. You can do all types of problem using the numerical method. So numerical method can solve any type of differential equation, ordinary differential equation. So Euler's method is the simplest, one of the very basic type of numerical method to solve the differential equation. Okay guys? Okay, let us see an example, the same example that we just did, and then see that for different value of the h, the step size, how the solution, how the approximation of the solution changes. Okay, how close it will be from the true solution. Okay, so our question is, solve dy over dx dt or dx equals to y when y0 is, let us write down t, dy over dt equals to y, and then y0 is 1. Use the Euler's method for h equals to 0.5. We did that by hand already. Okay, h equals to 0.1 and h equals to 0.01. I will do this by using a software called MATLAB. Okay, I will use this MATLAB and plot the true solution versus the true solution, that is y equals to e to the t, in MATLAB. So we will plot all these three different solutions with h equals to 0.5, h equals to 0.1, and h equals to 0.01, and then we also plot the true solution, which is y equals to e to the t, in MATLAB. Okay, so what are the things we will need to plot in the MATLAB is the initial condition, which is given, right? So t0 is basically 0, and y0 is basically 1, right? See that? But when we work in the MATLAB, MATLAB does not like t at 0, does not like the index 0. Okay, so what it likes is we will start from t1. So t0 is the first time point here. T0 is 0, right? And y0 is 1. Basically we are talking about this point. You see that? But when we write in the MATLAB, the MATLAB doesn't like the index 0. It doesn't like t0. Okay, what we write is, this is like the first point, this is the second point, this is the third point, this is the fourth point, and so on. Okay, that's why what we write is t1, the first value of the time is 0. That's what we write. So t1 is 0 and then y1 is 1. This is what we write. Okay, and also h, we will take h equals to 0.5, 0.1 and 0.01 separately, and n is the number of subintervals. How many subintervals do you want to make? Okay, and then after you decide that, we'll write a statement, for loop for n equals to 1 through n. You will do y equals to n plus 1, yn plus 1 equals to yn plus h times ftn yn. That's the exactly same Euler's formula. And then tn plus 1, you will update the tn plus 1 as t0 plus n times h. T0 plus n times h. That's what you do. And then you will so from this will create the order pair tn and then yn, okay? And then at the end we will plot t versus y, because y will be all the yn, t will be all the tn's, okay? So let me show you that. So what I'm trying to do here, so at the beginning I am plotting h equals to 0.5 and n equals to 5, meaning number of steps. How many steps do you want to make, okay? So for example, if you do h equals to 0.5 and n equals to 5, this is what it is talking about, because you have t and you have y, right? So this is t0, right? So t0 and then t1, that is 0.5, because h is 0.5. This is 0.5. t2 is, this is also 0.5, right? And t3, t4, 1 2 3 4, and then t5. So these are the steps, right? These are basically the h is 0.5, so this is 0.5, 1, 1.5, 2, and then 2.5. That's what we will see in the plot, okay? And then at this point we will find out the approximate value, okay? So this is 1, right? And then we will find the approximate value that the way that we did already. Okay, let me between starting with the distance between any two steps is 0.5, okay? y1 is 1. The 1 index is given because MATLAB doesn't like 0. That's why I'm giving y1 is 1. That is the very first initial condition, and t1 is 0. That is t at t equals to 0, the value is 1. That's the initial condition. And what we did for n equals to 1 through n, yn plus 1 is yn plus h times yn. Why that I did that? It is because f is y, right? dy over dx is y. You see that here? dy over dx is y there, right? So that is f, because the formula is h times ft and yn, but f is just y, that's why I wrote yn, okay? Instead of writing subscript, we are writing inside the parenthesis here, okay? And then tn plus 1 is t1 plus n times h. So here what we are trying to do is I'm plotting t versus y with blue. That's the approximation. And I'm plotting t versus exponential t. This is basically the true solution, okay? And this is the approximated solution, approximated points. Now I am running this, giving this is a blue color, and the real solution or the true solution are the red color. And line width is 3, which is the width of the line. Label is x-axis is t and y-axis is y2. If I run this, look at this graph. So the red one is basically the real solution, and then blue one is the approximate solution. You see that? This is a little bit different, right? The reason is because we have the step size 0.5. If we decrease the step size, then we will get better, meaning that this line will go close and close, okay? This is this is what I'm doing next, okay? What I'm trying to do here is I will plot this later, okay? And what I'm trying to do is, this is for h equals to 0.5. And what I wrote, I copied and pasted exactly the same code, except I denoted by y1 and t1. Here I denote by y and t. I'm denoting by y1 and t1. y1 and t1 is for h equals to 0.1, okay? At that time n is 25, meaning we will have 25 subintervals, because we want to see between 0 and 2.5, okay? And with each of the subinterval has width 0.1, h is 0.1. So I'm writing exactly the same code here. I copied that for loop. Only the difference here is I changed all the y by y1, okay, and then all t by t1. So if I run this, just plot both. You see that this is h equals to 0.5 and this is h equals to 0.1, okay? So what I will do is I will plot again for h equals to 0.01, and then I will plot everything together with the real solution. Here what I did is h equals 0.01, n is 250, because I want to see the x-axis between 0 and 2.5. So since the step size is 0.01, so I need 250 such subintervals, okay? I denoted by y2 here. So y21 equals to 1 and y2 here also, Okay, and what I'm doing is I'm plotting the approximation with h equals to 0.01 t2 y2 and then t2 exponential of t2. What I'm doing here is I'm plotting the real solution here at the end. Okay, so if I run this code, then what you get is, look at this. What does it say? Is this is the blue one is for h equals to 0.05. Okay, and then green one is for h equals to 0.1. Black one is, you see that 0.01, it is very, very close to the true solution. You see, so whenever you decrease the step size, then you will see your approximation will be close to the solution.